Welcome everybody to our webcast. Together with Laser 2000 partner SWIR Vision Systems, we will talk about high-definition SWIR cameras for machine vision and advanced imaging applications. This is our agenda for today. I will talk briefly about your host, Laser 2000, and give a short and general information about emissive and reflective parts of the infrared spectrum, which belongs SWIR to. Afterwards, I'll be happy to introduce to you Dr. Ethan Clem from SWIR Vision Systems. He will give us some interesting insight into high-definition SWIR imaging enabled by quantum dot technology. In the end, we will have a Q&A session with all the questions you have. To submit your questions, please use the chat function in the GoToWebinar control panel. We will make sure to answer all of them, either in the plenary session or afterwards via direct contact. Of all questions will be taken care of for sure. So, Laser 2000 has more than 30 years of experience in all facets of photonics. We work with manufacturers from all around the globe to provide local customers with their products. For this purpose, we do not only have contacts in Germany, but also in France, the Iberian Peninsula, and Scandinavia. We have also partners in the United Kingdom and Benelux. We attach great importance to advising our customers from A to Z in every stage of their project. In this way, we create the base for comprehensive, individual solutions that respond to every project, no matter how special. That is our know-how, that is our passion. Our wide portfolio allows us to provide our customers with every kind of photonics product, from laser safety via optics to fiber optics. Nearly every vision-related application doesn't rely solely on the cameras, sensors, and optical elements that are used, but also on the right illumination of the samples or the scenery. For this reason, let they be mentioned with Epilux and Genesi Electronica, only two of our partners for lighting solutions that can put your samples into the right light. When talking about infrared imaging, one has to take into account that there are several kinds of emissions. There can be types of radiation. There can be emissive types like mid-wave and long-wave infrared that are great for thermal imaging at elevated temperatures or with long-wave at room temperatures, as well as chemical imaging and gas leak detection. And then there is the NIR and SWIR region, which is, as the human visible spectrum 2, is more kind of a reflective type of radiation. Normally, there's no thermal emission at low temperatures or no infrared, shortwave infrared emission at low temperatures. So you need to illuminate the samples with the right wavelength or very broadband. But also, this region enables chemical imaging and moisture detection. Some advantages in the SWIR area are that glass is transparent in this wavelength range. So the most common and cost-effective materials are available. And a special point is silicon is transparent, which makes SWIR great for semiconductor inspection. But another point is that normal high-resolution silicon-based sensors, it's hard or nearly impossible for them to detect this SWIR lighting. And there are more transparent or interesting materials for the SWIR, like plastic and paints and many more. And here I will proudly present my co-speaker, Dr. Ethan Clem from SWIR Vision Systems. So welcome, Ethan.
Thank you, Martin, for that overview and introduction. Let's see, we're turning on the webcam here. It's great to be chatting virtually with your with this audience for this webinar today. Thank you, everybody, for logging in and attending. Excited to give you guys, everybody, an overview of some of the things we've been building here at SWIR Vision System in terms of the camera family and some of the kind of applications we're seeing our customers use, and then taking any kind of follow-up questions, and hopefully this can spark some ideas for imaging application challenges that you're facing in your work. So without, let's see, diving in here. So just to give you guys a little overview of the technology that we have. So oh, hold on, I think, oh, bear with me, some technical, we're good. I got confused by the page number. So just a very brief overview on a little bit about our image sensors. What we've brought to market is an image sensor that is essentially built around these type of newer semiconductor materials called colloidal quantum dots, and they're essentially a small semiconductor crystal, if you will, and we use those materials to form photodiodes, and use those photodiodes to absorb light that comes into the photodiode, excite electrons and holes and turn that into current, and that current gets amplified by an array of amplifiers in a readout IC and turns into an image. So in many ways, it's very similar to traditional image sensors like you might find with, for example, in a CMOS camera, where you have an array of silicon photodiodes detecting light and that being serialized and digitized and turned into an image. The difference here is that we build our sensors directly on top of an array of amplifiers without using the silicon material for any of the light absorbing. So all the light is absorbed in these layers of colloidal quantum dots. And so this brings certain pros and certain cons for the kind of image sensors that we could produce. I think one of the things that's very exciting about working with this material system is that it allows us to scale to very large areas and very small pixel pitches as well. So what we've done today with the technology is our first line of products is built around 3 formats of image sensor. We've got a 640, we call it, which is a standard VGA, 512 by 640, and then a 1.3 megapixel, and then a full HD 1920 by 1080. And this is an image of what one of our image sensors look like, and essentially think of it as a kind of a standard digital image sensor with a sensitivity that spans both the visible and the shortwave IR spectral region. And so what we're really excited about here at SWIR Vision Systems is that we've taken those 3 different basic image sensor formats. We've built a family of cameras, and our hope and our intention was to build a family of cameras that can be useful in industrial, primarily initially in industrial inspection and machine vision applications. So we've tried to include a feature set that should help the camera users and get up and running quickly and produce real meaningful data for their applications. So, roughly speaking, our cameras fall into 3 categories. We've got our standard SWIR cameras that I mentioned. And then more recently, we've released a couple of new additions to the family. We've got what we're calling a laser beam compatible SWIR camera, the L series. And I'll talk more about use of that camera in laser beam profiling applications in a few slides. And then we also have a new product family we're excited to release, which is eSWIR. So for us, the eSWIR in this camera has a absorption edge cut off at around 2,000 nanometers, 2 microns. And then it has sensitivity all the way through that shortwave IR, through the near infrared, and even down into the early part of the UV, you can see. So it's a very broadband absorber. Let's see. On to the next slide. So yeah, I'd mentioned the wavelength bands, and I think this is a nice little chart to show how the spectral sensitivity of our cameras compares to more traditional sensing material systems. So in the CMOS over on the blue end of the spectrum that we're all familiar with, does a great job in the visible region and can reach out to about 1,000 nanometers where the silicon band gap edge sits. And but as we know, frequently the sensitivity in the near infrared in the 900 region for CMOS is dropping pretty fast. And then into the near infrared, and then followed out into the SWIR, we have InGaAs, which I think is up until our technology came to market, was really the biggest show in town for people needing to do imaging in the kind of 1,000 to 1,700 nanometer range. So having this broadband spectral sensitivity certainly can provide, I think, advantages for some applications where additional information comes from both the visible side and the near and the SWIR pieces of the spectrum. So I kind of touched on this on the previous slide. Probably folks who've been working in the SWIR spectral band are familiar with InGaAs, and so it's important to point out that we're not. We've got some advantages and some I think some strengths compared to InGaAs, but we also have some weaknesses too. And so there will be shortwave IR applications where this is just the technology isn't a fit. But we're really excited to find that there's many great use cases where this technology seems to work quite well. So as I mentioned, I'll just quickly trot through these. We've got very high pixel count. As far as we know, we have the very first full high definition SWIR sensor available in the commercial market. The technology, although today in our commercial products is at 15 micron pitch, we really are excited about the ability to scale to much smaller pixel pitches. So we've done some demos in R&D programs where we've shown 3 micron, for example, and we're fairly confident that the limits for the pixel pitch are probably sub-micron region based on the way we manufacture our sensors and the way the way the electronic transport lengths and optical absorption lengths work in these material systems. I mentioned the broad operating spectral bandwidth. Just because of the material system and the manufacturing processes, we believe there's just a lower intrinsic cost than traditional epitaxial hybridization-driven processes that you find in InGaAs and mercury cadmium telluride and the likes. One of the great things with these cameras is that we have no ITAR, no restrictions for global export. And so that can ease shipping this product to customers who may have sites all over the world. Now, the minus here at the bottom is the lower optical efficiency. I'll show you in a few slides the quantum efficiency, that is the ratio of incident photons to extracted electrons in our sensors is lower than InGaAs today, although we are working quite hard to try to bring that number up. And so there's good hope there for higher quantum efficiency in the future. So just briefly, many of these applications, and I'll show, I've got some pictures and some that we can, we have later in the deck that show these use cases. Many of them will be familiar to folks in the shortwave IR. Essentially, I think where our cameras shine is where people have applications that there's a spectral signature they either need. They need to detect a chemical or detect moisture, or there's a additional contrast. Things that look white in the visible might be dark in the SWIR. And additional information can be gained by using that spectral region, and that's where it's really critical. And so, the machine vision generically covers a lot of different types of applications, but they include for us silicon inspection. Martin had mentioned how silicon is transparent to these shortwave IR wavelengths that these cameras can detect, so that allows inspection through a silicon wafer, either to buried features or backside features that may occur in stacked applications. The instrumentation and photonics, which kind of plays into laser beam profiling. There's a lot of infrared lasers being used for a lot of different, both industrial inspection and then and research and development. Lasers, abound, and so being able to see that beam with these cameras, it can be very, very helpful, very useful. Kind of changing gears, talking about surveillance systems, where you're looking at a broadband light source, you're outdoors, you're taking advantage of the fact that there's different atmospheric transmission characteristics, multispectral sensing, chemical sensing, some agricultural imaging, once again looking for contrast in agricultural products. And we're excited that we're at the early stage of looking at automotive applications for these cameras. And considering what we could do in the consumer mobile phone space as well. And finally, high resolution, high temperature thermography. These cameras are not good for sort of room temperature style applications that you'd see from traditional FLIR style bolometer imagers, but they're great for higher temperature, 200, 300 C and above applications. So some features of the cameras that we're shipping today is we have a TEC temperature stabilization. We actually don't usually use this to run the camera very cool, I should say. We tried it more for the stabilization that you would find in many SWIR cameras. So we often have the set point for the sensor to be at 30 degrees Celsius. So this cooling note is maybe a little bit of a typo. We're not really cooling that much. We're just making sure it's not running at 60 or 70 C, because the noise will degrade at those temperatures. We've got full visible to SWIR operating bandwidths. We've got both two flavors of outputs, USB 3 vision and GigE vision, a number of lens mount options. We've got a list of SWIR lenses available from our website. I'll talk a little more about that. And then we also send the cameras with a fairly straightforward software GUI that provides users ability to capture images and do command and control and stuff like that. So it's just meant to get people up and running quickly. Our thinking was that the SDK that we also provide would be the kind of software toolkit for people developing standalone software applications too. And finally, we have some pretty simple pixel non-uniformity correction tables that are built into the firmware of the camera. Here's a little more detail on some of the specifications of the performance. Here on the right is a quantum efficiency curve, and it really gets to that. I think it shows both the broadband response, we see 400 out to 1650, a little bit at 1700 nanometers, but also shows that the quantum efficiency in that red end of the spectrum is indeed lower than you would find in InGaAs systems. So InGaAs is up around 70 or 80% quantum efficiency. We're down around 10-15% quantum efficiency. And just to get right out in front of that, what that does mean is that InGaAs is ultimately more sensitive. So for really low light photon starved applications, these image sensors will struggle. But what we found for industrial applications so often, and many other applications, there's just a surplus of photons, and once you're kind of above the noise level of the sensor, which is actually quite good, then the image quality is fantastic. So I think anybody who looks at the QE curve and says, "Oh, I'm not sure that's going to work for me," I would want to understand, or I challenge them to first say, it's worth trying, because frequently you don't know exactly what the image quality is going to be until you put the whole system together, even if it's a mock-up or a kind of a demo system. And then the other point would be, if you do have the option of turning up the light. Lights are relatively inexpensive, and so add in a few more LEDs, or add in more halogen light, are ways to get more photons into the scene. So pixel pitch, frames per second, we've got, this is for the 640 by 512, pretty fast cameras with selectable bit depths for the digital out, fairly high pixel operability. The cameras are a snapshot global shutter. That's important to point out. We have an external trigger available for synchronization of the cameras with other equipment in a production or inspection system. A range of integration times that can be set. We actually have some firmware that can take this longer than the upgrade recently that takes us out to about a second for longest integration time. And then there's a firmware binning available. We think a good number of features that are implemented on camera for getting the image conditions and suited for the application. Let's see, a little bit about our lenses. This is kind of a screenshot from our website. I'd encourage everybody to go take a look if you have an interest or an opportunity. So we have a list of lenses that we can provide, and our applications engineers are happy to work with folks to determine what lens options exist and are recommended for the application. Suffice to say, it's exciting. There are more and more SWIR lenses available all the time, and so there's quite a good family of lenses for machine vision applications now. A little more on the mechanical and environmental specs here. We have an operating case temperature that we spec from -20 Celsius to 55 degrees Celsius. So I think that's fairly robust operating range for most industrial and even some outdoor applications. Power consumption listed here, DC supply range. We have a CE mark for regulatory, for safety, compliance, and what else do I want to point out? The power comes in along with a breakout cable for the trigger through a 12-pin Acuros connector. And once again, we have no license required. This is this ITAR-free designation. Okay, now we can dive into some one of my favorite parts, which is the imaging. And I think this is a nice slide that says, this sometimes it feels like this is an obvious point to make, but it's important to see these images. Like, what is the advantage that having more pixels, brings to an imaging application? And so this, is a simple but I think effective way of showing, simply put, for a given working distance from an object, more pixels gives you more field of view. You can see more of the object. And so, flip that around if you want to, trade off field of view for magnification. You can also get a lot more pixels in a smaller area by going to a more powerful lens. So, higher resolution or wider field of view, both of these things can be enabled by having more pixels. So I think one of the places where that, especially that idea of having a larger field of view, has really been important for our customers is in the silicon inspection world, where people are looking at wafers or die either after the fabrication process or midway through, and taking advantage of the fact that you can see here in the visible region, these die, they look like pieces of silicon. They're opaque. The visible photons are not getting in there. But then if you look at a SWIR illumination, if you're looking at photons that are beyond the band gap of the silicon material, you can see these buried features. In this case, this is a cavity of a ring for kind of a MEMS application where we've got two bonded wafers attached to each other with this metal seal cavity. And there again, like when you're looking at it, thinking about inspection, being able to inspect more die per exposure is really an advantage that just buys you throughput and buys you capacity. So I think that's one of the selling features of this technology that we have is the wide field of view. A little more on some silicon. This is where we've taken a higher magnification lens, like a microscope style objective, and we're looking through a wafer. This is through the top side of a wafer, and this is a buried backside alignment marks, and you can see the high resolution imaging and all the clarity. And so this can help for manufacturing and quality control. This is another neat application where instead of looking at the die from kind of the bird's eye view, you're kind of pitching it on the edge, and you're looking through the long end of the die, trying to see cracks that are occurring in the die itself. So cracks, and you can see there's a small little 5 micron wide, 100 micron long crack that's formed here. This is being illuminated from the back of the die into the camera using SWIR LEDs. And so this is another place where you're really taking advantage of the fact that those SWIR photons are able to give you information you're not getting in the visible. So that's a die edge for crack inspection. Let me page down. This is another example of that. Instead of a bare die, this is a die where bumping has been performed. So this is sort of pre-attachment to a circuit board. Here too, looking for defects in the edge, looking for the defects that show up as light is passed through that die edge into our camera. Flipping the wafer again, many wafers these days. There's many products, memory products, CMOS image sensor products where wafer stacking is happening, where wafer to wafer bonding is occurring, either for packaging reasons or circuit density reasons. And so during this wafer to wafer bond process, voids can form. And in the visible region with the CMOS, you're not getting any light through. It just looks like a black opaque wafer. But in the shortwave IR with one of our cameras, you can see like all of these voids that are where the bond between those two wafers, was not as desired. We had this wafer bonded. I think this might be a particularly bad example of a bonded wafer, but it really does show you what can be seen with these cameras. Okay, I'm gonna change gears a little bit, talk a little less about silicon, more about some kind of consumer packaging applications we're seeing. One of the properties of SWIR light is that many colored plastics are semi-transparent. They have much more optical transmission for these longer wavelengths than they do in the visible region. So here's a neat application where somebody was looking to see, hey, we've packaged this product, and we want to make sure that all of the candy was filled into all of the appropriate slots. And you can see, looking, with a standard visible camera versus a SWIR camera with an LED backlight, those photons go right through that cellophane wrapping, and you're able to inspect what's happening beneath that. We've got a couple of more examples of that. Here, I think this is an interesting way of sort of showing the impact of lighting and where the light is positioned. You know, the difference in the kind of data you get doing a backlight, which you see in the middle, and a front light, which you see on the right-hand side. You know, just different information that can be acquired there. And you know, here too, once again, we're taking advantage of the fact that many colored plastics have transmission in it. This is one where I think the plastics were a little bit thicker, and we were trying to see what was happening with a Ziploc seal, that kind of a zipper seal, plastic zipper, underneath all of that, all of the print that's on the surface, the colored plastic on the surface. This is for these dishwasher pods, wanting to make sure that both the vacuum seal and the zipper seal were present and complete. Kind of neat to see, you know, a great example of the, you know, I think the power of these longer wavelength photons, SWIR photons for plastics. We were using an Ephelux LED backlight for that. That's that square light you can see back in the setup there, and one of our cameras. So moving right along, this was some outdoor imaging, thinking about surveillance, safety, maritime safety. In particular, this was an example where we had a customer looking to use these cameras for ferry boat operation. And we were doing some imaging on the coast, and a big rainstorm came in and really just obscured the visibility across this inlet, this 3-kilometer inlet. And we looked down at the SWIR camera imagery that we were getting, and we realized that, wow, we were getting much better transmission through that rainstorm. And this is just a function of the particle size in the air and the wavelength of the photon and scattering that occurs as those photons move through those particles. This was an early image with one of our early 640 cameras, but it was pretty exciting to see this kind of use case. Here's another example of outdoor long-range imaging. This is a summer day with some kind of classic summertime haze. This camera, one of my colleagues was up on North Carolina mountain here, looking out across a forest, and you off in the distance, about 36 kilometers away. I was going to say 23 miles. 36 kilometers away is a city line, and that is really quite visible with the SWIR camera, but it's just hard to make out in the visible region. And this again is an example of longer wavelength photons having different scattering properties off of atmospheric obscurance. Oh yeah, this is a neat picture. This is like thicker plastic. Now we've got a lot more plastic, not just the cellophane, but you know, all the plastic you would find in a thick laundry detergent bottle. And we've got a backlight where now the liquid laundry detergent is absorbing a lot of shortwave IR photons because of typically where the water absorption occurs at around 14, 20 nanometers. And you see a pretty clear fill line with the SWIR, and it's much harder to make that out with the visible. Food sorting. Speaking of the water absorption, I think we found for food inspection, one of those kind of classic use cases for SWIR is wanting to use that shortwave IR absorption of water in 1420. Region where the water essentially starts to absorb and looks dark. This is a bruised red pear, and you can see where the fruit has been bruised under the skin of the pear. Water has started to pool. It's more moist there, and the photons penetrate just far enough into beneath the skin to be more strongly absorbed, and you can see that bruise very, very clearly. We have a picture of walnuts where we were using a very narrow 1200 nanometer notch filter to try to provide contrast between the fruit, the heart of the nut, and then the shell, which in the visible, shades of brown are difficult to distinguish, and this nut sorting packaging company was excited to see that you could definitely see more contrast, and started to build an application around doing shell inspection with these wavelengths. Vial fill, where you want to take a transparent liquid in a transparent vial, for example, in pharmaceuticals or in medical testing, where you might have like a saline or something like that. Use it. This application, we have an LED backlight that's getting absorbed by the fluid, so you can see the dark saline, and then but being transmitted through other parts of the vial, and you can do an inspection for the fill level. And then in this case, they were concerned about having the label present, and we're able to work through the label as well. It looks like we have maybe a little bit of PDF image drift, but you get the idea here. So this is an application in the mining industry where a mineral that's used in the production of potash for fertilizers is being mined, and the concern was being able to distinguish good material from material that is actually kind of dangerous to the mining operation. It looks like a very similar color, but can absorb moisture very quickly, and leading to dangerous circumstances because of the moisture uptake. It changes the stability of the material while underground. And so in this SWIR image, you can kind of, I'm trying to make out, you can see these dark veins are showing where the bad material is. The white stuff kind of in the background, and you can even see color contrasts. It's just different absorption properties, distinguishing where the good material is, taking advantage of that dark water absorption that I mentioned. Yeah, I think this is an exciting application. I think mineral processing and mineral sorting, certainly using the shortwave IR and more the extended SWIR as much as the standard SWIR out to 2.5 microns, I think has been well known in the satellite aerial imaging world for quite a long time for doing aerial imaging for minerals. And so this is neat to see how that same spectral region can start to be translated to industrial operations, in this case underground. Okay, this is a neat application where some folks were doing plastic welding. They were welding two plastics together using a near infrared laser as the welding, as the heat source, and needed to be able to see a near infrared absorbing coating that they were using to enhance the welding process. But with our standard visible cameras, they weren't able to see this coating, but with one of our SWIR cameras, you can see an example where, because of that absorption of that coating, we get a lot of contrast, and then that can be used as part of the welding process. So most recently, I'm gonna kind of change gears and talk a little bit about laser beam profiling. I think we've got a version of this camera where with the L designation that we have, that is suitable for laser beam profiling. I think it can serve as kind of the engine for our laser beam profiling system. And in fact, we're very excited that another one of Laser 2000's partners, a company called DataRay, has in fact incorporated our camera into a new laser beam profiling product. Kind of a little plug for DataRay here. Using where they are using that SWIR sensitivity for doing 1550 nanometer beam profiling. Because of that broad spectral range, you can use it for many different laser colors, and we're also looking to be doing the same thing for our extended SWIR product. Certainly more information on that to come. I believe they might even be giving us another one of these webinars in the future. So yeah, stay tuned. We're excited about DataRay on that product. This is an image of hot glass. So this is where you're not using reflected light, but you're using emitted light, thermal photons that are coming, in this case from glass that's 300 to 400 degrees Celsius, using the different intensities light to get information about the quality of the glass that had just been produced. We have a video of this on our website of these hot glass bottles coming out of a furnace, and so you can see the same kind of imagery, but real time with at video rate. This is a neat application. I think high temperature, high speed thermal imaging is a really good fit for this technology, and it's one where many other technologies, traditional bolometers, for example, really struggle with that high speed triggerable part of a camera system. Let's see. Yes, this is a little bit where we have a customer in Switzerland in Bern, Monsieur Kufner, who has been using these cameras for looking at through the pigments of images of paintings to look at features that were put down by the artist beneath that final layer of paint that the world sees. So you can see the sketches of the outline, and they're using these cameras in this art history context to get more information about the artistic process and potentially people who are involved in it, and it's really very interesting, and we look forward for more of these kind of images to come out. And I think here too, this is a case where having more pixels, having higher resolution is very valuable to this kind of application for larger canvases and for finer details. If you go over to our website, we have a little white paper on this, and it provides more information on what was being done and why and what was learned. So yeah, please do take a look at that. Okay, we're coming near to the end of the slides. I know there's a lot of material here. We're excited about this one. This is a newer kind of an emergent application for us. We've made these large industrial cameras, and so we never really intended for them to kind of go into like a headlight assembly or behind a windshield on a rearview mirror, but we can use them for getting information about what does this image sensing technology provide for new information in an automotive use case. So this is one where we're looking at the difference between a visible camera and our camera on a foggy day, providing contrast between objects on the roadway or in the vicinity near the roadway. And we have a video of this also on our website that I'd encourage you to go and take a look at if you have a few minutes. This is some imagery from our extended SWIR product. So this has this very broadband response out to 2 microns. We've got an image with a 1650 nanometer long pass filter. So we're really just looking at photons from about 1650 to 2000 nanometers. There's actually another water absorption band out at just past 1600. 1690, I believe, and so you can see how dark that water is absorbing. You can see the very different transmission characteristics of the aluminum anodization. Those are differences, and yeah, we're excited about this SWIR camera product because it is high, as I said, high resolution, and it doesn't require any deep cooling. So room temperature operation is fine. So with that, I think we're coming to the end. I got over time a little bit. I appreciate everybody who stuck with me, and I think we'll turn it over to Martin, who can help to field some of your questions our way. So yeah, thank you for your attention so far. And Martin, yes. Back to you.
Yeah. One moment, I'll be back in an instant. So I think now I can be seen again, which may be good, maybe not. But yeah, thanks for this great presentation. I hope it was interesting for the audience as it was for me. But I already got some questions that I want to share with you. and I hope we can discuss these questions in detail. Some other questions, yeah, will come to you or to us depending on the location of the question poster. That will be answered directly in the aftermath. But yes, so let's start off maybe with the first one. So I think I know you had it before, and I think I can take this question for you. So how does the SWIR sensitivity compare to Inga sensors? So as
Sure.
Ethan said before in his presentation, the sensitivity or the quantum efficiency is lower than Inga sensors, but there's still some potential to get this up. I think Ethan can tell more in which regions you can get with these sensitivity ranges.
Yeah, that's a great question. So this is a great question, and it's an important question. So as I maybe touched on briefly previously, you know, for standard SWIR in gas that stops at 1.7 microns, in that SWIR region of, let's call it, you know, 1100 to 1700, we have very similar noise, but we've got approximately, you know, 1/5, 1/6 the QE, and so the minimum sensitivity, like the minimum number of photons needed to get above the noise level of a pixel, is going to be about roughly directly proportional to that. It's going to be, depending on the color, it's going to be 1/5 to 1/6 or 1/7 depending on the wavelength. So that's where we are today. As Martin alluded to, actually one point I should add, however, is that the pixel size will be important. And so when you have very small pixel in-gas sensors, like there's some we're starting to see come onto the market, you know, but as that pixel size shrinks for in-gas, you're just getting less signal than you would for a larger pixel. And you know, that's true in any imaging system. And so for very small pitch in-gas, our you know, like for 5 micron pitch in-gas, our 15 micron pitch SWIR, the larger pixel area essentially compensates for the lower QE. And so the amount of signal you're going to get in an imaging system, for all conditions being equal, from a tiny pixel in-gas to our 15 micron pixel in-gas will be the same. If you're comparing apples to apples, 15 micron in-gas to 15 micron CQD, we will have lower sensitivity. But as I said before, we have found for time and time again from many applications that only matters when you're like really pushing the limits of the camera because of really low photon flux environments. And once you're above the noise level, the image quality is great. Oh, finally, I wanted to add, we are working really hard on improving the QE. And so I think within, you know, nobody hold me to this, but within the next 1 to 2 years, we're going to see at least double and maybe triple kind of QE sensors that we're going to be bringing to market.
Great, thanks for your answer, Ethan. And yeah, let's see if we get the next question live as far as can get. So otherwise, I'll try to tell it before. It takes some seconds. There is it. Okay, so there was a question from the audience, especially thinking of from a hyperspectral imaging point of view. So is there an option to software trigger the camera by frame? So I think yeah.
If I understand your question correctly, so yes, there is a software trigger feature. It doesn't, not just hardware trigger, there's also software trigger, and you can trigger a single frame event. That's another setting within, whether you trigger a free run event or X number of frames. and it can be single frame. So I think the answer to your question is yes, as long as I understand what you meant by the biframe. And if I missed that, please follow up with a follow-up question via email or otherwise.
Yeah. I got another question during your presentation, which should come in some seconds. This is one of the parade question, of course. How does the cost of your SWIR sensors compare to InGaAs sensors of the same size?
That's a great question. So we have that. So first, for specific pricing and delivery inquiries, please reach out if you're in Europe, if you're in a country in Europe where Laser 2000 represents us. Reach out to your folks at Laser 2000. If you're in another part of the world, we have distributors in other places, and we'd be happy to work with you to give you specific pricing information. Generally speaking, all of our sensors, especially for the same size, are far lower. We like to brag that we've got the lowest cost per megapixel. It's all relative. We're not selling these cameras for CMOS sensor, prices today yet, but you will find that for an HD SWIR application, that the cost per megapixel is much lower, and our VGA is lower too by quite a good chunk. And as I mentioned, these are single unit kind of volumes, and once we talk larger volumes, all the pricing information really scales in a very exciting kind of way.
Okay, so let me just put on another question. It's more of a technical one. So what temperature can be cooling? That's a point. So where I can start to answer and give it later to you. I think by default the cooling is set to 30 degrees plus 30 degrees Celsius. So that you don't need any additional or enhanced convection to get the heat off of the sensor. But yeah, you're able to define other lower temperatures, and that's the point where Ethan has to step in. I don't know if it's that cold, so minus 20, but you will have to make sure the heat gets away.
Yeah, I mean, simply put, we really have a very simple, we've got a single stage TEC in the sensor that's, referenced against the case temperature. So, the cooler you can get your case temperature through active cooling means the cooler you can get your sensor temperature. So we have one customer, for example, that runs the sensor at 15 degrees Celsius, and they do that simply by having a fan blowing on the case to pull off the extra heat. If you wanted to go as far as attaching the case to some kind of liquid cooling plate, a cooling plate of some kind, something that would provide a lower kind of reference, then you absolutely could get down to the temperatures you're talking about. It's going to take some mechanical engineering on your end, just because we just have a single stage TEC in there. So that's kind of a half answer to your question, but yeah, hopefully that gives you enough to think about. And let's do follow up if you want to follow up on this topic, please.
Yeah. So another one coming here. There was just dropping a lot of question in, so I have to concentrate a bit to get everything managed here. But yeah, let me just paste this one here. Maybe should come any second. So have you experienced more interest for machine vision applications and medical bio recently? And what do you think is the biggest barrier, like pixel resolution and pixel size?
Interesting question. Okay, so yes to the top part. We've certainly experienced more interest in those silicon 3D stacking flip chip, etc. We've had less engagement with fluorescence applications in medical bio, although we've had a little bit. I think what we're hearing from our customers about what would be better for those 3D stacking and flip chip, they would like more pixels and they would like smaller pixel pitch. I feel like probably more pixels is driving harder than smaller pitch. And so right now we're looking at developing a roadmap for what does the next generation of cameras look like, and I would be happy to hear from customers and potential customers about what would be important for their application in terms of format and pitch. As I said, we have a lot of flexibility to go in really any dimension as far as pixel size and image sensor size, and so just knowing what's important to the community is valuable. For fluorescence, I think there I don't have a lot of direct experience with that, but generally many of the fluorescent signals can be relatively weak. It's a multi-photon process before you're getting that photon back out with lots of places to lose energy along the way. And so I think fluorescence, probably the sensitivity is going to be the biggest challenge there. But as I said, we don't have a lot of customers working on that right now. So if you've got a fluorescence application and you'd like to know more, please do reach out.
Great, and I see we're running to the 1 hour boundary, I think. So we'll have one or maximum two questions, I think. Yeah, the questions here are stacking. Yeah, this is an interesting question because yes, I was thinking about this as well. So, are you planning to launch line scan cameras with CQD technology, or can the current ones be used as a line scan?
Great question. So as of today, we have no plans, no short-term plans to launch the line scan cameras with CQD technology, not today. But we're always happy to have conversations and understand if people think that there is a strong use case or a short path to get there. But so as of today, no short-term plans for line scan. The cameras can be windowed down, however, and you could certainly use, and we've got some customers who are using sort of sub portions, and as you window the array down, your frame rate goes up. There are some limits to that. The reset time of the ROIC, for example, provides a cap to the frame rate. So yeah, I think the camera, like if you wanted to turn it into 100 color push broom hyperspectral, where you've got 2,000 pixels wide with 100 pixels tall, for example, that the camera can absolutely be configured for, and it can go smaller. Some of the dedicated line scan cameras have 15 kilohertz, 30 kilohertz frame rates. The camera will not be able to push those kind of frame rates. So reach out with specifics of what kind of line scan configuration you had in mind, and we can give you specific feedback on what can be achieved with that camera.
Okay, so I think we have time for one last question that's concerned with the silicon die etch pictures that you showed on on your presentation. So it was slide 21, 22, but it's hard now to get back to these to have these slides shown. I just want to paste this question here, but yeah, just so let me get this question maybe by hand here Just yeah, it's
real time.
Die edge inspection. Yeah, which lighting has been used? And I'm pretty sure I know it because I had it.
You know it too. Martin, you want to take this one?
Yeah, sure. So for these slides, I had that set up in Germany lately. It was an Acuros lighting, so LED 1550 lighting, very powerful, and used together with a Navitar optics, and yeah, that works pretty good. The power is very high, and even I experienced when using this, I can go with the lowest, yeah, with very low power and still have the integration time on the lower end of the range. I think you experienced similar.
Yeah. My colleague Alan Hilton did that setup here, so I didn't have my hands on that one. So your experience sounds very similar to his. Yeah, the Acuros light is fantastic, as is the Navitar lens that they had for the high magnification lens. Yeah, no, I think that's a really good application for these cameras, and I think you could, with the right kind of balance between optical throughput on the lens and optical power from the lamp, you can run these cameras, at very fast, short exposure times for really high speed inspection applications for just that, for example, just that use case for example, yeah.
Okay, so I think we reached the 1 hour mark for now. So I think we will close this session now, but please, all the questions that haven't been asked or cleared here, we will share the questions with your regarding distributor or partner or SWIR Vision Systems and have it clear all, and you will be contacted. Hopefully, yes, or definitely with the right answers that will help you. And now I'm proud to present our next webcast on the 10th of November. So please feel free to stay tuned and to register for compact and cost-effective UVC emitters, which are used for disinfecting water, air, and surfaces. Very important due to the COVID crisis we're facing right now everywhere. And yeah, co-hosted by our partner Chris Lyas. And so we may wish you all the best and stay healthy, everyone. And thanks for joining us today.
Yes, I'd like to really thank the whole marketing team and the whole team at Laser 2000 from SWIR Vision Systems here for putting this together. Thank you, Martin. Thank you, Marcus, in the background there, running the show from behind the curtain. This has been a great opportunity for us. We're really happy to be here, and I also want to thank all the folks here at SWIR who helped put all of this together. I just get to be the person talking about all the exciting results. But it takes a whole team here to do the work. So thanks to everybody here at SWIR and there at Laser 2000 and folks in the audience. Hey, reach out if you've got questions about SWIR or whether these cameras would work for you. We'd love to chat and figure out if this is a good fit for your needs.
Okay, thank you and your team. Bye.